Dear students, today we are going to discuss about inertial and non-inertial frames of reference. So far you have learnt about Cartesian coordinate system, you have learnt about polar coordinate system, spherical coordinate system, you have also learnt about cylindrical coordinate system. All these coordinate systems are used to describe an object, its state of rest, or its state of motion, or these are used to describe an event. By event, we mean any kind of happening. So, all of these coordinate systems are called as frames of reference because it is with respect to these frames that you are actually specifying or describing a given event, a particular event, right? Now, for example, if I say that I have moved 5 kilometers, this is not a proper information, a complete information, unless I don't say that I have moved 5 kilometers from my home to my office, say, for example. And then I have to also add certain parameters that I took this much of time, my vehicle moved with this much velocity, my acceleration was this much, and I was moving in the north direction, for example, right? So, this I am able to do by describing, by specifying this event with respect to a particular frame of reference. So that gives a complete description, an exact description of the event, because we cannot choose to describe events in air. We have to begin from certain point, a referral, certain point. And that frame is called frame of reference. Now it depends on the kind of event, that what kind of reference frame should we choose. If an object is moving in a linear motion, it is exhibiting a linear motion, then we understand that Cartesian coordinate system would be suitable. If it is moving along a circle, we understand that polar coordinate system would be suitable. If the object is moving along the surface of a sphere, then this coordinate system would be more suitable. Otherwise, this would be suitable, and so on. Moreover, these frames of reference can themselves be at rest or these can be in motion. For example, if someone is trying to locate me by standing at a particular point, say a tree, a building, a monument, anything, so he is trying to describe me from a rest frame of reference. But a frame of reference can also be in motion. For example, when I choose to go by bus or by a plane or by a train, all of these are frames of reference, but they are moving. Similarly, when we go in rocket, when we go in spaceships, all of them are frames of reference, but they are moving. So a frame of reference can be at rest or it can be in motion. Now we choose to classify these frames of reference in broadly into two categories. One is inertial and another is non-inertial. Remember, the frames of reference in which Newton's laws of motion hold good, that is, they are valid, are called as inertial frames of reference. And the frames of reference in which Newton's laws of motion get modified are called as non-inertial frames of reference. So Newton's laws hold good here, they are valid here. Here, they become slightly modified. Now, inertial frames of reference are those frames which are either at rest, remember, either at rest or possessing a uniform motion. Uniform motion. That is, they have a constant velocity. Once the velocity is constant, what is acceleration? Acceleration is dv by dt, that is 0. Non-inertial frames are those frames which have an accelerated motion and not a constant motion, remember. They are not moving with a constant velocity. The first thing is that non-inertial frames are always moving frames and they are not moving with a constant velocity, but they have certain acceleration, right? Now, even if you have a rotating frame that is rotating with a uniform velocity, even then it is non-inertial, because we know that in case of rotation, centripetal acceleration is still associated with the system. We know that F is ma, And in case of centripetal force, this is written as mv square by r, right? So that, what is this v square by r? It is the centripetal acceleration. So even if a frame is moving with a constant velocity, it still does have an acceleration, and that acceleration is called as centripetal acceleration. Therefore, uniformly rotating frames are also non-inertial. Let's choose the example of Earth, for example. So we know that Earth is at a certain distance from Sun. And what is the distance? It is 15 crore kilometer. You should remember that. What is the velocity of Earth at each point of this circle? It is obviously velocity is 2 pi r, that is distance traveled by time. And we know this is r will be given by this much, 15 crore kilometer, and in terms of meter, that is how much? 1.5 into 10 to the power 11 meter. And t is the time taken in one complete revolution, that is 365 days, 24 hours, 60 minutes, 60 seconds. And when you calculate that, it comes out to be this much. This is the velocity of the Earth around the Sun along its orbit. Now, what is the acceleration? Because it is a circular motion, there will be a centripetal acceleration. That acceleration is obviously v square by r. So, v square, we have already found that. And r is again this much, 15 crore kilometer, 1.5 into 10 to the power 11. And this comes out to be 6 into 10 to the power minus 3 meter per second square. And this value is quite small. Because Earth has an acceleration associated with it, it is actually a non-inertial frame of reference. But since the value of this acceleration is quite small, we treat for all practical purposes Earth as an inertial frame. For all practical purposes, Earth is treated as an inertial frame, but in a more particular sense, since there is a centripetal acceleration associated with it, Earth is actually a non-inertial frame, right? Now, we have to describe these inertial and non-inertial frames one by one. In today's video, we'll try to finish the inertial frames, and in the subsequent video, we'll talk about the non-inertial frames. Now, as I told you that inertial frames can either be at rest or they can be moving with a constant velocity. And the first important thing is that we have to conserve physics. Our aim should be that the laws of physics did not change, the output of the results did not change, whether we observed an event in a rest frame of reference or in a moving frame of reference with constant velocity. So, therefore, to connect an event which happened in a rest frame of reference with an event which happened in a moving frame of reference, of course, moving with a constant velocity, that is the condition. There is a certain set of equations which are called as Galilean transformations. And Galilean transformations prove that laws of physics, the output of results or experiments, does not change because of the fact that the frame of reference was at rest or in uniform motion. Now we shall see that, suppose this is a frame of reference which is at rest and we denote it by S, and this is a frame of reference which is in motion with respect to this S. So this observer is O, this is O dash, and this frame of reference is S dash. Now choose any point. Suppose R dash is the position vector from this frame of reference and R is the position vector from this frame of reference, right? We can also choose to join these two. Remember that S dash is moving with the constant velocity, and that is the condition. Constant velocity u, for example, with respect to S. S dash is moving with the constant velocity u with respect to S, right? Now it is moving with the velocity u, and I'm showing it this way. So this distance will be ut. Velocity into time, distance, this distance. So you are writing that r dash plus ut, if you use the triangle law of vectors, triangle law, this plus this is the resultant. So r dash plus ut is equal to r. So we are actually, let us differentiate both. So dr dash by dt plus u, because this is a constant, this is equal to dr by dt. Now dr by dt will represent it by v dash, that is the velocity of the particle in the moving frame of reference, and this will be the velocity of the particle in the static frame of reference. Then we take this u to other side. So this is the relation. This is the equation that connects the velocity of the particle in the static frame of reference, velocity of the particle in the moving frame of reference, and this is the velocity of the moving frame itself. So velocity changes. It doesn't mean that velocity of the object change. It is from the perception of the observer. For an observer O, the velocity is v, this particle. And for the observer O dash, the velocity of this particle is v dash. But of course, the object in itself is moving with certain velocity. It is only the difference in observation, in perception. And that arises because we are observing the particle from two different frames, right? Change in velocity doesn't mean that velocity of the object has changed. This change actually reflects the value that is estimated by one observer and the value that is estimated by another observer. Now let us see what happens to other parameters. Suppose coordinates and time and acceleration and force. So let's do that. See, so we can move to next page. So what did we write? We wrote that r dash is equal to r minus ut. This, I'm talking about this equation, that r dash is r minus ut. So you can from here pick the components of, for example, if this was the point and its coordinates in s are x, y, z, and the coordinates of the same point in s dash are x dash, y dash, and z dash. Now let us see how do we connect the coordinates of the point, of the same point, from two frames of reference, and we'll make use of this. So x dash will be x minus uxt. Y dash will be y minus uyt. And z dash will be z minus uzt. Because of course this u will basically be uxi plus uyj plus uzk. Three components. So taking the clue from this equation for r dash, because r dash is the position vector, right, of the particle, of the object in the moving frame of reference. So when we connect it to coordinates, this is basically x dash, y dash, z dash, x, y, z, but u will also be written in terms of its components. So these are also called Galilean transformation equations. Now let us see what happens to, for example, length of an object. Length of an object. Suppose we have an object whose length is this much, and how do we find this length? Essentially by subtracting the coordinates of the endpoints. So length is x2 minus x1. Therefore the length in the moving frame will be L dash is x2 dash minus x1 dash, right? So for this x2 dash, you can write it is x2 minus vxt or uxt basically, using these equations, minus for x1 dash, you can write it is x1 minus uxt again. So this and this will be plus, it will get cancelled with this. You are again left with x2 minus x1 only. So L dash is the same thing as L. This means that length is a Galilean invariant. Length is invariant. Therefore, even from the perception of two observers, whether in the moving frame of reference or in the static frame of reference, the length of the object comes out to be same. It doesn't change. The only thing that changes from the perception of the two observers is the velocity of the object. Length does not change. So let us see what happens to acceleration now. Again, we'll make use of this equation that v dash is equal to v minus u, right? We obtained that somewhere here. We obtained this equation, v dash is v minus u. So from here we can find acceleration by differentiating it with respect to time. Obviously this is a dash is equal to a, because this is a constant. Because the velocity of the moving frame is constant, this will be 0. So a dash is equal to a, right? So acceleration is, again, we can write that acceleration is invariant under Galilean transformation. Galilean transformation. Now what about other things like force? Because we know that force is ma, and since acceleration is a constant, that is, acceleration was invariant, it didn't change under Galilean transformation. Mass is already a constant, so F is a constant. It doesn't change with Galilean transformation. Therefore, what we have learned essentially that Galilean transformation is a set of equations that connects an event in a frame of reference at rest and that in motion. But this Galilean transformation does show us that acceleration, mass, force, the parameters that are needed to describe an event, these do not change. Length, etc. Length, acceleration, mass, force. And because force is the basic thing that describes the motion, acceleration, it describes the motion. So the net results of an experiment or the laws of physics, they do not change. And amongst these, the most important parameter is force, because we know that Newton's laws of motion is equal to, is this. See, the first law of Newton and the third law of Newton are basically that they can be deducted from the second law. The actual law of motion is actually the second law of motion. F is equal to ma. So once F is constant, m and a are constant, the results of an experiment do not change by transforming from a frame of reference which is at rest to a frame of reference which is in motion. In the subsequent video, we will take up the description of non-inertial frames of reference.